So in talking about Pascal's recurrence and Pascal's triangle, we always write things like n choose k. But remember, this is actually equal to n choose n minus k, for the simple reason that if I'm going to choose a k element subset from n objects, I can either choose the ones to put in my subset or the ones not to. So maybe less hidden notation would be to write it like this. We're still only choosing k things, and then we have sort of everything that's left. But when we write it like this, it becomes a little more clear that we have this symmetry. And this is the symmetry that we notice on both sides of Pascal's triangle. If we flip it side to side, we get the same thing. That's not the same as the unimodality property that we just did, but it's an interesting symmetry property that it has. So this begs the question of how we could generalize this. Instead of having two things, two categories in the subset or out of the subset, why not have more? So that's going to be the generalization that we're going to look at today. So if we're going to take integers, say a1, a2, all the way up to ak, and these need to be non-negative integers. It's okay if they're 0. It's a little ridiculous if they're 0, but that's fine. And we want to have them add up to some specific amount, a1 plus a2 plus ak is equal to n. This is sort of like these two guys add up to n. I want all of these guys now to add up to n. Then I'm going to define a symbol, which is n, choose a1, a2, ak, and this is simply going to be, it's kind of the same thing. I'm going to choose sets, but now I don't just get two sets that are complementary to one another, I get k sets. So this is the number of ways to choose a1 things for one set, a2 for another, all the way up until you have ak for the last. And we've seen this actually before. There's a theorem that we did a while back, but maybe I'll leave this as an exercise. Prove that n, choose a1, a2, ak, generalizes the expansion that we have above. So maybe we'll do that one first. This is equal to n factorial divided by k factorial n minus k factorial. And the reason it's nice to write it with a multiple notation is because we get a1 factorial, a2 factorial, all the way up to ak factorial. So this is nice. This gives us a way to kind of generalize the binomial coefficients to these multinomial coefficients. Maybe I'll write that down. Multinomial coefficients. And then all the things that we know about the binomial coefficients have nice analogs in this paradigm. So let's think about a few of them. What do you think happens if we add up all of the multinomial coefficients? Well, we can get that from a generalization of the binomial theorem. Remember, that was sort of our all-powerful thing. So for all n and k that are non-negative integers, we have the following. We need to have a lot of variables for this. x1 plus x2 all the way up to xk. That's a lot of different variables raised to the power n. This is going to be the sum of all of these coefficients. So we're going to have a1 plus a2 all the way up to ak equals n. All different ways of writing n as the sum of these numbers. We put our coefficient in there, a1, a2, ak, and then we have exponents for our x's. So this turns out to be an incredibly convenient thing for analyzing different, if you have a bunch of objects of different types 1 up to k, right? This becomes very convenient. But you can see there are lots of natural corollaries that fall out of this that have parallels to in the binomial case. So if I just add up those coefficients, if I take the sum of a1, a2, plus ak equal n, and I add up the multinomial coefficients, what do I get? Well, by the binomial theorem, I've just set all my variables equal to 1. So I just get k to the n. So in the case where k equal 2, that's the binomial case, and I'm getting 2 to the n, but I can get powers of 3 this way. And in fact, this is a nice way to do committee problems. And you can do all the same combinatorial interpretations that work. You just now, instead of having 2 options, you can have 3 options, 4 options, all the way up to k options. This is something we're going to look at again at the end of the semester when we do some card shuffling. It turns out that the binomial coefficients are very nicely related to shuffling with 2 hands, but if you want to do an octopus shuffle, then these guys can come in very handy, as it were. There's also, I won't draw it in just because of my lack of skills, but we can think about Pascal's prism and their recurrence relations that generalize the Pascal's recurrence that apply in this multinomial setting. So this is something that's going to come up time and again. It gives us a convenient way to do some computations. Usually when there's a problem that's going to involve these multinomial coefficients, we're not actually going to evaluate it because it takes a really long time to do. But we could, if we needed to, throw it on the computer at the very least and figure out how many things there are.